Hi everyone, my name is Yunran Yin, and this is our final presentation of DSCC 265. And we have a team of 5 people, and they are Chen Yao, Naman, Yiwei Han, Han Yangzhang, and me, Yunran Yin. I'm just gonna do the introduction and data description part. So our topic is about heart disease prediction, and we looked into like a very unbalanced data set of heart disease risk factors. We were really interested in this data set because we know that there are many risk factors that contribute to the heart disease, and which is like kind of like a really leading causes of death nowadays. And since most of the causes are medical or like lifestyle related, so we believe that it's very critical to use computational techniques to analyze patterns in data sets and make predictions. So our data is kind of like really unbalanced and has 319,000 rows and 18 columns. And there are 13 categorical features and 4 numerical features used to predict the target value. We want to use several like models. Actually, we used 3 in the end, and we're going to introduce it later. So we use like 3 models to predict heart disease based on patients' health and habits. We want to use regression analysis to find out which variables in the dataset have the greatest impact on heart disease, as well as the relationship between the two. So we are attempting to accomplish 2 primary goals here. So with this project, so to begin with, we want to kind of make accurate predictions using the best model developed from the dataset. We also want to draw conclusions from this dataset about which variables are more likely to cause health attacks. We found the following essential hypotheses from the dataset that I think they are BMI, smoking, alcohol consumption, stroke, physical health, mental health, and age. So yeah, this is the introduction of our project, and then we did a correlation matrix. So to optimize the model, we want to see like a visual representation of variables that have like a strong correlation with the prevalence of the heart disease before we pre-process our data. So in the graph, you can see that the darker the color of the graph, the more closely related and stronger the correlation relationship are. So according to the relationship matrix graph here, I think it's kind of like fairly obvious that the following kind of sets of the variables like general health, diabetic, yes, no, smoking, stroke, physical health, age category, and kidney disease have like a strong relationship with the data set. So as a result, we kind of will concentrate on these like categories more in our following models as well. So the next we also did like included like a comparison of heart disease and the general health in our study. So we discovered that like there's like a strong correlation between the two. So the worse of your heart health condition will be, the greater you're gonna have like a better possibility to have like a heart disease. Yeah. So next we have like 2 graphs here. They are kind of like possibility of heart diseases with like a gender, and also like if you smoke or not. So we can see from the probability that males are more likely than women to suffer from heart disease, and it's about like 1.6 times more likely. Men are more like 1.6 times more likely than females to suffer from the heart disease. And in addition, I think we can also see from the graph here that, and also the probability that more females went tested from the data than men. And also from the smoking probability, we can see that there's like majority of the heart disease patients do smoke, and also that people who smoke are more like about 2 times as likely as those who do not smoke to develop like heart disease. Yeah, so that's like introduction and data description part. Next, we will have Yue Han to tell us more about pre-processing part to our data. Thank you.
Now we start the data pre-processing procedure. There are 4 steps in the data pre-processing procedure: data quality assessment, data cleaning, data transformation, and data reduction. For the data pre-processing procedure, first is we need to check to see if there are any missing values in each column of the data set. Surprisingly, the data set is clean and there is no missing values, so we did not need to do anything and use the method like fill-in-A. In order to transform the raw data into more useful format, we use one hot encoder to implement categorical features. This can partition each category with each features to different columns. For the category of each row lies within, it would use 1, and the ones that not use 0 to indicate. It is basically a Boolean partition. For example, we added columns such as no smoking and yes smoking, and implement binary results into the dataset and drop the original column named smoking, which has yes or no. We use this procedure to every variable we think has important effect on the actual results. This method is also useful with columns that has many categories. For example, we can partition the columns H category to many columns like 55 to 59, 65 to 69, etc. Each column has one category, and for the tuple that lie within that category, we label 1, and for the ones that are not, we label as 0. Then we import the label encoder to target the column heart disease and fit it and return the encoded label. This label encoder makes the no transform to 0 and yes transform to 1. This will be used in the future train test split and prediction model. Now, after doing the label encoder, we were able to standardize the features with actual numerical values in each column of the dataset, such as BMI, physical health, mental health, and sleeping time. Standardization procedure could be shown using the equation C equals to X minus mu over sigma. Specifically, the z-score is calculated by each data point minus the mean over standard deviation. The idea of this is that after performing standardization, we could eliminate the differences in scale of different columns, which produce a well-shaped form before using them in models. Now we are moving to the next step, which is splitting the data into training and testing set, and we would use the oversampling method. Our data set is very imbalanced, and looking at the data set, we see that nearly 91% of the data comes from individuals with heart disease. This leaves us with a significant smaller ratio of healthy individuals when compared to individuals with heart disease. So it would be more likely for our model to predict someone without heart disease. To prevent the bias in the dataset, we decided to oversample the unhealthy individuals. The oversample data produces a more smooth gradient signal. Instead of showing each positive example in a single batch with a large weight, they are shown in the many different batches, each with a small weight to demonstrate the concept.
So this is Hanyang Zhang. I'm going to do the model parts. So first, for the random forest package, we use the random forest as one of our models because it is a classification algorithm made up of many decision trees. When building each individual tree, it employs bagging and feature randomness in an attempt to create an uncorrelated forest of trees whose prediction by committee is more accurate than any individual tree. Each individual tree in the random forest predicts a class, and the class with the most votes become our model's prediction. We understand that some trees may be incorrect during the prediction process. Many other trees, however, will be suitable so that the trees can move in the right direction as a group. The classification accuracy of random forest model was in the test was 0.76, which was pretty good. Typically, the accuracy is not the metric we use to judge the performance of a classification model because of the imbalance of the data. Therefore, we use a confusion matrix, which is a way to express how many classifiers prediction were correct and where the classifier became confused when prediction was incorrect. We also have F1 score, which for two classes is 0.85 and 0.34. And we use F1 to determine whether or not a classifier is effective at defining members of the class in which it is trained. The details will be shared in the results and evaluation section. Next model we are using is the logistic regression package. This method, which commonly acknowledged as one of the most efficient linear classification methods, in a nutshell, logistic regression is a tool used for discovering the relationship between the dependent variable and the independent variables. One advantage of such regression is that it could handle more independent variables, which helps us to make more predictions. And the package we're using here is from sklearn linear model. It is pretty straightforward as we set the parameter random state to 0 and implement trained and tested variables. In order to explicitly analyze the significance of such variable in datasets, we made a table which contains the largest 15 coefficients for the variables to see which one have the higher or lower impacts. The details will be shared in the results and evaluation section. And last, for the deep learning neural networks, our deep learning method is one of our choices because it is the most effective methods for processing large amounts of unstructured data. Deep learning can be implemented as a complex model for numerous parameters. So to begin, our model has 3 layers: the input layer, the hidden layer, and the output layer. The input layer's vector is set to be 48 in this example. Then we created a hidden layer that set a vector to 30. We are aware that as the number of hidden layers increases, the depth of the layers increases. However, after increasing the number of hidden layers, the accuracy of the result did not improve significantly as we hoped. Consequently, we decided to stick with a single hidden layer throughout. After that, the output layer was set to 12, and the eta was set to 0.1, and our function was programmed to run 10,000 times in total. The cross entropy loss between the input and the target is computed using the criterion, which is defined as, in addition, we use SGD to optimize the new weight. In addition, we set the learning rate to be the same as the eta coefficient. Then we use alt equals to model x, as is shown here, to test out the prediction of the column. Then use torchmax to have the biggest number, and the details of the result will be shared in the result and evaluation section. And Yao Chen will discuss the result part of the project.
Hi, this is Chen, and I will talk about the results of our 3 models. Our models include the logistic regression, neural network, random forest. Also, the accuracy seems to be high with 92% almost. But I think it's pretty normal to reach this kind of accuracy because almost 90% data points are in the category of people who are healthy, which means 90% of data points are in category 1. So it's very normal to reach this kind of accuracy. So I think accuracy is not the perfect metrics for imbalanced data set. So we also did recall analysis, but without doing any special treatment, for example, oversampling, our recall is not very high for our models. I will talk about the result with oversampling data, but I will show the result of the model without oversampling. So this is a result without the oversampling. As we can see, F1 score for class 1 is on the right of here and here, here. As we can see, they are not very high compared to accuracy. So, which means we had a hard time to identify a person who actually have heart disease, which is not good in order to save life. But based on this model, without doing any oversampling or undersampling or any special treatment, we also have some special coefficient for logistic regression. I think the number of coefficient is reasonable. Like for age category, if a person is older than 80, then the coefficient is largest, which makes sense, I think. Yeah, and we post the top 50 coefficient here. Yeah, so let's talk about the result with oversampling. After oversampling, which is a special treatment for imbalanced data, our accuracy dropped largely from 92% to 75, around 75%. But instead, we get some good F1 scores, which means we can better identify a person who actually have heart disease. So based on this model, we can save more life maybe. As you can see, the F1 score is from 0.0 something, 0.01 to almost 0.3. So our F1 score also increased largely. And based on this model, the top 15 coefficient of logistic regression are shown below. Similarly, the most influential variable is also the age category with age older than 18. And second one is age from 75 to 79, and so on. So basically, we did our model by two methods, with sampling and without oversampling. Why do we want to do the oversampling? Because we want to increase our recall and F1 score so that we can better identify a person who actually has the heart disease. So it's second pro of the oversampling. Better find out people who has heart disease. But there are some cons, like the accuracy will decrease, and by doing oversampling, there are some risk of overfitting to the class of minority. Okay, that's all. So Naman will introduce our conclusion.
Hi, my name is Naman Barar. I'm here to break up on the conclusion section of our project. Now, tying back into originally the goal of this project, we wish to set out and study the factors that were related to predicting heart disease with our models. And we also had mentioned and touched upon earlier the usage of oversampling. So I'm here to discuss how that actually ties into our conclusion and what we had found with that. Now, looking at the overall accuracy, we see that there's a significant drop-off without oversampling than we see when we go to our oversampling models. We see that without oversampling, the model that is the most accurate is actually our logistic regression. However, once that accuracy has gone down because we move to the oversampling, we see that it drops off. And actually, in terms of accuracy, the most viable model to use would be our random forest. Moving away from this, we see the results of our logistic regression models for our cases without oversampling. Now, what we notice here, looking at just the top 5 categories of these top 15 coefficients, we see the age category taking the first, second, and third, with our 4th place being given to general health, and then our age category going and rounding out the 5th and 6th categories in terms of their importance. So what that means for us is that it seems to suggest that age does play a very significant role. Additionally, having an overall poor general health does contribute to our model's prediction of an individual's potential for heart disease. And we do see other factors such as stroke and age category coming up later on and lower on in this list. However, it seems to suggest that above the age of around 60 to 65 is where that condition does become very important to consider alongside general health. Comparing this to the results of our logistic regression model when we had the oversampling present, we see once again a slightly similar trend. The first place, second, third, and 4th in this case are being given to an age category variable. We see that obviously, once again, age plays a role in this situation. More importantly, we see once again, general health is important as the coefficient is higher in this case than it was previously. However, age still follows up. This leads us to believe that overall, age and your overall health play a very significant role, at least according to our models. We do see other factors coming in here, such as the age category following up for 60 to 64, the stroke history definitely playing a greater role once we have done our oversampling. Additionally, we see other factors come up. However, it still seems to be consistent that age, general health play the most significant roles based on their weighting as a coefficient. Moving beyond this, we feel that there's a lot that could be learned from this and can be applied in different sections. Specifically, when these predictions need to be made, age category should be considered as a priority along with an individual's overall general health.